In this video, we're going to talk about the effect of the reactant concentration on the rate of a chemical reaction. So we're looking at data for this chemical reaction here. Nitrogen, dinitrogen pentoxide decomposes into nitrogen dioxide and oxygen gas. And what we see is at the beginning of the reaction, when our concentration of N2O5 is about 1.1 molar, if we want to know the instantaneous rate at this point, we'll look at the slope of this line that's drawn just tangent to this particular point at 1.1. We see that the slope of this line is fairly steep, and that tells us that the rate is fairly fast when the concentration of N2O5 is 1.1 molar. Now we'll check it out when the reaction has proceeded for a little while longer. Here, when the reaction has proceeded for a total of 7 hours, the concentration is now 0.2 molar, right about here, of N2O5. And we see at this point the instantaneous rate, that's the slope of this line here, is not as steep. It's a lot more shallow. And this tells us that the rate of the reaction is much slower at this point than it is at this point. That is to say that the rate is slower when the concentration of the reactant is lower, and it's higher when the concentration of the reactant is higher. So therefore, we see that the rate of the reaction is proportional to the concentration of the reactant. The rate's faster when the concentration of reactant's higher, and the rate's slower when the concentration of reactant is slower. This is a common thing that's seen in chemical reactions. The reactions slow down as the reaction tends to proceed. And from this information, we are able to assume the following. We assume that the rate of the reaction of a chemical reaction, rate of reaction, is going to be equal to some constant K, we call this the rate constant, times the concentration of the reactants. In this case, we're going to call our reactant N2O5. That's what we saw in this reaction here. So the concentration of N2O5 raised to some power N. So it could be like the first power, second power, or something like that. Now the question is, how do we find what the power of N is? Well, if the reactant concentration doubles and the rate doubles, this goes up linearly with this, and in that case, N would be equal to 1. So if we have the rate equals K times the concentration of N2O5, we see here if we double the concentration, goes from 1 to 2, the rate will go from 1K to 2K. Increases concentration, increase the rate by the same proportion, then N is going to be equal to 1. There are some cases where this changes. There are some cases where N is 2. So in that particular case, we'd write this. And here, if we doubled the concentration, we would quadruple the rate. Because if we put a 1 in here, the rate is going to be K times 1 squared, which would be 1K. And if we put a 2 in here, double the concentration, 2 squared is 4. Doubling the concentration, the rate would be 4K. We quadruple the rate from K to 4K. So let's see if we can see how this sort of plays out. Let's say we've got our reaction, N2O5, decomposes to 2 moles of NO2 and a half mole of oxygen. And we note that the rate happens to be 1.4 times 10 to the minus 3 molar per second when the initial concentration of N2O5 is equal to 0.3 molar. And the rate is 2.8 times 10 to the negative 3 molar per second when the concentration of N2O5 is 0.15 molar. Excuse me, 0.6 molar. You should notice that this rate here is twice this rate here. And this concentration is here is twice this concentration here. So it's a 1-to-1, you know, this goes up with the same proportion. This doubles, then this doubles, then n is going to be equal to 1. And in this case, we would say the rate is equal to some concentration K times the concentration of N2O5 to the first power. And we'd write the rate law like that. Now, sometimes you can just figure this out by looking at the data. Other times it's a little more difficult. So how do we find the rate law in these more difficult cases? What we use is this particular equation. We find the value of n by doing the following. We take the natural log of the rate measured under the first condition divided by the rate observed under the second condition. Notice we take this ratio and then we take the natural log of the ratio. And then we divide this by the natural log of the concentration under the first condition divided by the concentration under the second condition. That's really mathematically what we're doing. So let's apply this to a particular example. Once again, we're going to use our reaction. N2O5 goes to 2NO2 plus half O2. And we'll notice that the rate is 2.8 times 10 to the negative third molar per second when the concentration of N2O5 is going to be equal to 0.3 molar. That's condition 1. And then under condition 2, we notice that the rate is 7.0 times 10 to the negative 4 molar per second when the concentration of N2O5 is going to be equal to 0.15 molar. Now, it's pretty easy to see that this represents a halving of the concentration, but I'm not real sure what is going on here with the rate. So let's use this equation to see if we can't find what the value of n would be for our rate law. So we'll use this equation. We know that n is going to be the natural log of rate 1, which we're going to call this 2.8 times 10 to the negative 3 molar per second. And we'll divide that by the rate under condition 2, which is 7.0 times 10 to the negative 4 molar per second. These units should cancel. Anytime you're taking the natural log of something, what you're taking the natural log of should be unitless. These should cancel, and they do. We're going to divide this then by the natural log of the concentration under condition 1, which is 0.3 molar. And of course, we'll divide that by the natural log of what we see under condition 2, which is 0.15 molar. Once again, the units cancel, which they should, for anything that we're taking the natural log of. Now we need to do the arithmetic. So I'm going to do the top fraction first, 2.8 times 10 to the negative third, and we'll divide that by 7 times 10 to the negative 4. That's 4. So on the numerator, we're going to have the natural log of 4. This divided by this is 4. Here, I hope you see that 0.3 divided by 0.15. Well, that's 2, isn't it? So in the denominator, we're going to be taking the natural log of 2. So what's n going to be equal to? Let's see. N is going to be equal to 4 natural log 1.386 divided by natural log of 2, 2 natural log 0.69. So 1.386, divide that by 0.69. Looks like n is 2. And so if this was indeed the data, or these were indeed the data that we collected for this particular reaction, what we would say is in this particular case, the rate law would be rate is going to be equal to K, some rate constant K, times the concentration of N2O5 raised to the second power. This formula is going to help you finding N in any of these cases. Okay, we just found for the last reaction that the rate is equal to some rate constant K times the concentration of N2O5 raised to the second power. We would call this the rate law for our experiment, for our chemical reaction, the chemical reaction listed here. Now, because N is equal to 2, what we would say is that the rate law is second order with respect to the concentration of our reactant N2O5. There are certainly other possibilities that can exist. For example, we might have a rate law that looks something like this. The rate is going to be equal to some concentration K times the concentration of NO to the second power times the concentration of chlorine to the first power. And in this case, what we would say is the rate is second order, here's the 2, with respect to the concentration of nitrogen monoxide. We'd say that it is first order with respect to the concentration of chlorine, and we'd add these two together, and we would say the reaction is third order overall. So to recap, this particular rate law, we would say the reaction is second order with respect to the concentration of nitrogen monoxide. It's first order with respect to the concentration of chlorine, and we add these two together to get the overall order of the reaction, which we would say is third order overall. And there's a number of rate laws that can be, rate orders, I should say, that are determined for various rate laws. So how do we figure out what these rate laws are? Well, they have to be determined experimentally. You have to run an experiment in order to determine what the rate law is for a particular chemical reaction. So how is this done? Well, let's look at these data here. All right, let's say we're studying this reaction, the reaction between carbon monoxide gas and nitrogen dioxide gas to produce carbon dioxide gas and nitrogen monoxide gas. And we'll say this reaction was studied at a certain temperature. You got to keep temperature constant because chemical reactions, the rates of chemical reactions are highly dependent on temperature. So we keep the temperature constant. And then what you do is you start with varying concentrations of the reactants, because that's what you're trying to do. You're trying to say, okay, how fast does this reaction go depending on how much of this we have present and depending on how much of this we have present. And so you vary the concentration of each species. These are, it's a little hard to see here, but these are the concentrations of carbon monoxide in units of molarity. And these are the starting concentrations of nitrogen dioxide in concentrations of molarity. And these are the resulting rates. And you see you have a variety of concentrations here, And of course, as you vary these, the rates are going to vary. And what we're going to want to get when this is done from these data, we are going to want to get some expression that says the rate of this reaction is going to be equal to some rate constant K times the concentration of one of my reactants, carbon monoxide, raised to some power X times the concentration of my second reactant, NO2, raised to some power Y. And we're going to use that equation that we had before. Remember, we'd find the order of reactions, the X or the Y, by taking the natural log of rate under condition 1 divided by rate under condition 2. And then we're going to divide that by the natural log of the concentration under condition 1 divided by the concentration under condition 2. So we're going to use this to find X and Y here. But we have to be careful about how we do this. When we are trying to find how the reaction varies with the concentration of carbon monoxide, we're going to want to vary carbon monoxide concentrations between two runs, but we got to keep everything else constant. You don't want to go changing 3 or 4 things between 2 experiments. You only want to change one thing. So what we're going to want to do, we're not going to want to compare these two because you're not varying carbon monoxide. If I want to find out how the reaction varies with carbon monoxide, I'm not going to compare experiment 1 and 2, but I sure might compare experiment 1 and 4. Now, before I check to see if I'm going to use experiment 1 and 4 in my equation for N here, I have to make sure that even though I'm varying the carbon monoxide concentration, I'm not varying the nitrogen dioxide concentration between the 2 runs. So the concentration of nitrogen dioxide had better stay constant between runs 1 and 4. And let's see, in run 1, the nitrogen dioxide concentration is 0.35 times 10 to the negative 4. And hey, look at that. It's the same thing in experiment 4. And so I can compare experiments 1 and 4 appropriately to find how the reaction varies with respect to the concentration of carbon monoxide. And so I'm going to do that. So let's see. We're going to do rate 1 and rate 4. So that's going to be 3.4 times 10 to the negative 8 molar per hour. So that's rate 1. 3.4 times 10 to the negative 8 molar per hour. And we're going to divide that by the rate under condition 2, which in this case is just condition 4. 6.8 times 10 to the negative 8. Molar per hour. We'll divide that by the concentrations of carbon monoxide under the two conditions, which is 5.1 times 10 to the negative 4 for condition 1. That'll be molar. And we'll divide that by 1.02 times 10 to the negative 3. Now, if I do the math here, the hour per hour cancels the per hour, the molar cancels the molar, 10 to the negative 8 cancels 10 to the negative 8, 3.4 divided by 6.8, that's a half. So I got the natural log of a half over, oh, there's a molar here too, that'll cancel. If you run the math here, you'll see 5.1 times 10 to the negative 4 divided by 1.02 times 10 to the negative 3, that's also the natural log of 1/2. Whatever that is, it's going to, this divided by the same thing, that's going to be 1. Now again, what we were checking here is how the concentration of carbon monoxide varied. And so what we did is we found the value of x. We have found here that the value of x is equal to 1. Now we're going to need to do the same thing for y. We need to find how does this reaction vary when we vary the concentration of NO2 but keep the concentration of carbon monoxide constant. So I'm going to let you look at these data here and think about what trials can we compare to find how the concentration of NO2 affects the reaction. In other words, what's the value of y in this rate law? So I hope you recognize we are going to want to do some runs in which this concentration varies, but this concentration remains the same. And it's pretty easy to see experiment 1 and 2 does this for us. We just ignore all the others. We see that in experiment 1 and 2, our concentration of NO2 varies. And between experiments 1 and 2, these stay the same, which they must. Only one of the concentrations should vary when you're doing this trick. And I hope you see that, these will cancel. 10 to the negative 8 will cancel if I divide this by this. Basically, what you're seeing is that between experiments 1 and 2, as you double the rate, you go from experiment 1 to experiment 2, look what happens to the concentration. Doubling the concentration doubles the rate. Anytime you see that, you know you have a first order reaction. You can run through the math. You can use this equation too, but what you'll end up with in the end, is y is equal to 1. And I'll leave that for you to do. But what we're able to write at this point then is the rate is going to be equal to some rate constant k times the concentration of carbon monoxide to the first power times the concentration of NO2 to the first power. So we would say that this reaction is first order overall with respect to carbon monoxide, first order with respect to nitrogen dioxide, and 1 plus 1 is 2, so it's second order overall. We're not quite done. because we want to find out what is the value for K. And to do that, what we will do, the actual numerical value for K, we'll pick the data from any one of these that we want. We'll plug them in to this equation. We'll be able to plug in the rate. Let's just do that. We'll plug in the rate. Let's just do it for experiment 1. We can choose any one we want. I'm going to pick experiment 1. So for experiment 1, we'll notice that the rate is 3.4 times 10 to the negative 8 molar per hour. So I'm going to plop that in here. 3.4 times 10 to the negative 8 molar per hour. That's equal to K, and we want to know what K is, times the corresponding concentration of carbon monoxide, which is 5.1 times 10 to the negative 4. That'll be units of molar. And then we'll plug in the corresponding value of nitrogen dioxide. Again, we're using all experiment 1 here. 0.35 times 10 to the negative 4 molar. I know this. I know this. I know this. I can solve for that. So I'm just going to divide both sides by both of these values. This will cancel this. This will cancel this. We'll find our value for K on this side. And then, of course, whatever I do to this side, I have to do to this side. So we're also going to divide this side by 5.1 times 10 to the negative 4 molar. And we're also going to divide this side by 0.35 times 10 to the negative 4 molar. I'm going to check my units. This molar cancels this molar. I have a molar that survives on the denominator and an inverse hour that survives. So the units are going to be per molar per hour. And now all that's left to do is the math. So on the numerator, I take 3.4 times 10 to the negative 8. I'm going to divide that by 5.1 times 10 to the negative 4. And I'm also going to divide by 0.35 times 10 to the negative 4. It looks like I get 1.9. That's the value for K. And so overall, I can write my rate law is this value for K, 1.9 molar per hour times the concentration of carbon monoxide to the first power times the concentration of nitrogen dioxide to the first power. That's my rate law for our chemical reaction here based on these data here.